Welcome to another RDWorks Learning Lab. Now, I've been in that position for quite a few hours over the past few weeks since I discovered the way in which laser beams and lenses work together to produce a cutting effect in materials. Now, as I've said to you several times before, I've done a lot of research and I couldn't find any information about how that mechanism worked. So I had to try and work it out for myself. And I had that light bulb moment. And from that light bulb moment, I began to realise that I'd stumbled on something much bigger than just the cutting properties of lenses. This is not prepared stuff, as usual. We're going to go out to the machine and we're going to test some of the ideas that I've had. And I'm pretty confident that we're going to come up with some startling revelations. Lens theory has been around for 400 years, well proven, well tested. But lasers have only been around maybe 30, 40 years. And yes, it is light, but to slightly paraphrase Mr. Spock, it's not light, Jim, as we know it. And that's the problem. And that's what we're going to investigate today. I've been playing with this technology now for about 6 years. With the kind assistance of Cloud Ray, I've amassed a fairly comprehensive collection of lenses. And about 2 years ago, I did a fairly large test on many types of lenses. We're in the position where we only have 2 types of lens that we can buy for this machine. We can use them this way or that way. We've only got 3 types of material that we can use. Zinc selenide Chinese style, zinc selenide USA style, and we've got gallium arsenide. There are several more lens types than this, but these are the typical ones that you come across and I've got in my collection. Well, if we multiply those together, we find that we have 60 possible combinations of lenses to test. I've tested almost all of those, but to buy, well, you've only got to buy 2 lenses, but you've got to buy them in 3 materials and all these combinations of focal lengths. So I've got a huge amount of experience playing with these lenses. To be honest, none, and I mean 0, have come close to matching the claimed specification for these lenses. And that's the basic premise behind today's session. Why can't I get anywhere near the specifications that are claimed for these lenses? Arguments would be, I haven't got my machine set up properly. Well, hang on, I've got 6 years experience and I've done quite a lot and understand exactly how and why you should set a machine up. So I don't think that's a valid excuse for me. Are my mirrors clean? Is my lens clean? Well, I change my lenses so often that, they don't get a chance to get dirty, and I check them every time they come out. So none of the excuses that are generally offered for why we might not achieve the specification of a lens are valid in my case. I've been very careful because I'm trying to meet that specification that's claimed for these lenses. Now, my suspicion of lens theory and how it applies to laser machines started about 2 years ago. If you look at all the conventional lens diagrams, you'll see that various focal lengths here have got different spot sizes, as they call them. Well, that's basically the point through which all the light rays pass. That's the diameter at the focal point. It can never be 0. It always has to be something. And depending on the focal length of your lens, that something is represented here in millimeters. Okay, now if we convert those millimeters diameter into areas, and then we change the areas into just a relative number. In other words, if I regard that number for a 1.5 inch lens as being 1 area, then for a 50 or 2 inch lens, the spot size is 3 times the area, 6 times the area, and 18 times the area for a 4 inch lens. So let's assume that I've got a 60 watt laser tube and I'm trying to work out something called the energy density per unit area. What it means is that for an area of 1, I've got an intensity of 60 watts per unit. The energy density drops off considerably as I increase the focal length of the lens, and the spot size increases. That means I should be able to cut faster and deeper with a 1.5 inch lens. No, that's not how it works. It turns out you can cut a lot deeper with a 4-inch lens, and you can cut basically a lot faster with a 2.5 inch lens than you can with a 1.5 inch lens. So there's something seriously wrong with this idea of energy density in the spot size. And that's where my whole mission of trying to understand just what's going on with lenses started. I began to realize that the important factor in cutting was light intensity. In the previous section, light intensity was sort of described as energy density. I don't like the word energy density because it doesn't convey the right image. Intensity, you understand exactly what it means. Brighter and brighter and brighter. Now I know our laser beam is invisible, but in the invisible spectrum there is still this concept of brightness. I began to realize that the shape of the beam was a very important factor in efficient cutting. Now here I've got my tube. It's a C70 from a company called SPT, who make very good tubes, and their specification are always honest and open. They underspecify rather than overspecify. So I love this particular company. There are several critical factors that we need to look at that help us decide on the quality of a tube. The most important being this one here, beam quality. Now it says less than or equal to 1.1. Here we've got the intensity distribution of a pure Gaussian shaped beam, and this number 1.1 refers to how close the beam matches this theoretically perfect Gaussian form. And in the case of this tube, it's 1 divided by 1.1, which is 91%. So it's a pretty good match for this intensity distribution. Now let me just redefine this graph that you're looking at here again. This is a graph of the intensity of the beam against the diameter of the beam, and the area underneath this graph is equivalent to the power that you're putting into the beam. It doesn't have to be this tall and it doesn't have to be this wide. It will always have the same mathematical proportions. This is my beam. If we have a proper Gaussian form, we have the ability to change the intensity of the beam by changing the power of the beam, because we're keeping the footprint, the base, the diameter of the beam exactly the same. So because we've constrained the diameter of the beam, what will happen is we will actually be increasing the intensity of the beam. And that's the key thing that I discovered about how the beam operates. So let's look at this thing here, spot diameter, 5 millimeters plus or minus a millimeter. Now what does that mean? Well, that means that what we're really talking about is what the manufacturer claims the beam size to be. So if I've got the choice of 2 specifications to use, would I use the big one or would I use the small one? So I think that my beam is specified as this, something called full width at half maximum. So there's maximum power, 50% of that, and then that's the width of the beam at 50%. Now this beam shape here, which is a Gaussian beam shape, is defined by something called TEM 00. There's a whole load of these transient modes. This is the burn that all glass tubes aspire to copy. There are uses for these other modes, which we're not going to go into here. If it looks like this at the low end of the specification, there's a problem with the tube, and it immediately tells you you've got a B grade tube. A good A grade tube will never look like that. It will look like this all the way up from virtually 0 power to full power. Now the next thing we're going to have to look at is this thing here called beam divergence, because it's something that everybody ignores, but it actually has a significant effect on the performance of your machine. Glass tubes have got a very small beam divergence at around about 3 millirads. If you go for something like an RF laser, that will have a beam divergence that could be up as high as 7 millirads. Now what the hell is a millirad? If I draw a very simple triangle, the triangle will be 1 millimeter tall after 1,000 millimeters. If I've got an angle in there of 1 millirad, and bear in mind my beam diameter is supposedly 5 millimeters, but probably 10. Let's assume we start off at 10 millimeters, and we're going to have 3.1 millirad growth in the beam per meter. The machine that we're going to be using is 600 by 400 millimeters. So I'm expecting to see 3 millimeter beam growth between the back left corner and the front right corner of my machine. You can say, so what? Well, this is where this picture is so informative. So there's my 100% power, 70 or 60 watts, whichever number you want to choose. If I increase the footprint by 3 millimeters, which is 30%, the area under the curve is going to remain the same. So, but it does mean to say that the maximum intensity that I'm going to get is now going to drop down by maybe to here. So this is now going to be my maximum intensity. The area of that red bit is the same as the area of that black bit. But look what it's done to the intensity. I've lost cutting power. I have to keep re-stressing this, but you must remember that the damage to material is all to do with the vibration of molecules. The more intense the light, the greater the speed at which you will be able to accelerate the vibration of those molecules. You'll be able to vibrate the molecules to destruction. The greater the intensity, the faster we should be able to make that destruction happen. This graph is a dual purpose graph because not only does it help you to imagine what's happening to your beam as you change the percent power, this happens to be a plot of a 10-second burn with my beam. And it shows clearly that the high intensity at the center is having a greater effect than the lower right at the outside of the beam. So if you blunt your beam, your cutting effect will be less. So as I move from the back left corner of my machine to the front right corner, I'm expecting to see a reduction in the cutting capability of the machine. Now, taking the lens tube out, we're going to put this safety receptacle here right at the front of the machine. And now the laser beam should fire down into my coffee. Yes, it's explosively boiling the coffee. So I'm just going to hang a piece of masking tape just here. I've gone full power, so I've got to be very careful that I don't set fire to this. The quickest pulse possible, like that. And there we go. You can see I've already burnt a small hole in there. We'll keep the pulse on just a fraction longer. And you can see it caught fire, but that's not a problem at the moment. We'll just stop those from running away. As I increase the exposure time, I'm allowing the lower intensity part of the rays at the outside of the beam to have a burning effect. With a short exposure time, they will have no effect. As I hold the beam on longer, on, and I've just stopped those from running away. Now hold it on, stop them from running away again. On. Now you can see, look, we've gradually got some burning around the outside there. Did you see that low power gradually come in as I exposed them for a significant amount of time longer? Now, this is at the front of the machine. If I open the side door of the machine, we should be able to see it from here. Right. On, 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 So let me crudely try and measure those. 12. And this, well look, we've got to go right out to the extreme. So this is 15. So there's our 12mm sharp beam, and there's our 15mm slightly blunter beam. We've got more of a halo, a scorch halo around the outside, which we couldn't get with this. This was a clean burn. That was not a clean burn. I can't believe this is even a 5mm beam at half width full maximum. Now, if you were doing cutting, you would have your beam on for substantially longer than I had that beam on. So this would be the diameter of the beam that was hitting your mirrors and arriving at your lens. And this is only a 70-watt tube. We're now going to run one of my speed tests down at this front right-hand corner. You will see that we get a very short exposure, and then the exposures start to grow by about 2 milliseconds per pulse, and you'll see the depth of cuts getting gradually deeper. A bit more difficult to line things up on that back corner. Well, let's just hope that we're lined up. Well, it's certainly not going to be easy for you to compare those results visually. So I've done it for you. Now, you may well find that when you're using your machine, cutting down at the front corner is not as good as it is at the back corner. And here's the reason why. Beam divergence. Now, it's exactly as I predicted for you. Now, I'll be honest, I've never done this test on the machine before. So this is a little bit of a surprise to me that there is so much difference between the front and the rear corner. Now, I normally work down towards the front corner because it's easier to work down there. But I'm now going to start working from the top left-hand corner because, hey, I get much more efficient cutting there. Look, I'm probably at least 15 to 20% more efficient. Now, why is this? The beam is small here, and as we've shown with our burn test, we've grown by at least 3mm when we get to this front corner. And growing to 3mm bigger means the beam is bigger. For the same amount of power, I'm not going to get as much intensity because the area under the graph is exactly the same, which means it reduces the height of the graph, i.e. the intensity of the beam. And material damage, i.e. cutting, is all dependent upon beam intensity. There is no more obvious statement of this fact than this graph. Now we've thoroughly investigated the beam and how it changes its size as we use different parts of the work table, we're now going to start looking at some lenses. Here we've got a Plano convex lens, and it's used here in a way that nobody recommends using a lens, and that is convex side down. And you can see why. It's a hell of a mess. The rays go all over the place. And here we've got something called an image plane. This is quite an important word, image plane, that we've got here, because this is something called aberration, spherical aberration. It's because this shape here is part of a spherical surface, and no matter how perfectly you manufacture that spherical surface, it will have this physical weakness. It will conduct rays of light all over the place when you use the lens this way round. Here is the range of spherical aberration. When we change the lens to the other direction, wow, that's a significant improvement. The rays are behaving themselves because they're nearly, but not quite, meeting up at something that you would consider to be a focal point. You can see the rays from the outside are still not matching up with the rays from the centre. We've still got spherical aberration even this way round, but it is substantially less. Now theoretically, if you use a compound lens like this, for which we have those lenses, remember, we've got positive meniscus lens like this, and we've got a Plano convex lens like this. Now I know it doesn't look flat because of the way in which your eye is dragged by this surface here, but trust me, that is a flat surface and that's a convex surface. And this is basically what my compound lens looks like. And it appears that this has the ability to focus right down to a single point, which is perfect. A focal point. Whether it's as bad as this or like this, and you can see we've got that magic word again, image plane. I'm going to refer you to a wonderful document that I've recently discovered. I earnestly ask you to go and have a quick look at this document. This professor here was talking about lens aberrations. This is all wonderful stuff. Look at those formula there. They mean nothing to me. My knowledge of optics would fit onto one side of a grain of sand. Here's what spherical aberration does to an image. It makes it fuzzy. It makes it out of focus. This is a very important concept that we're looking at here. Not the fact that it's out of focus or in focus, but the fact that we're talking about an image. When you look at these pictures, it clearly says on here, image plane. Image plane. My results have never come anywhere close to the claimed specifications that I read about for lenses. Why? Now, when I look at these two images, a whole new world has opened up to me when I combine this with my understanding of how lenses cut. This is working backwards into that much bigger problem that I told you about at the beginning. This is lens theory at its best. Ray projection. Uniform light projecting images onto a plane. You saw from the previous images how aberration affects the focus. Question number one. Is there a focus here? No, there are all sorts of focal points here. And we've still, even this way round, got all sorts of focal points. We are not trying to project an image. We are trying to project damage onto a plane, not by light ray focus, but by intensity focus. Now, they might sound the same, but in reality, they are totally different. A light ray focus, as we can see here, is fixed. But I can assure you that you can change an intensity focus, because these rays here are not the same intensity as these rays here. And all this mess in between is a mess of various intensity rays. Somewhere in there is an intensity of light which will do damage at a certain speed and power. The two things are completely independent. You can increase the power and change the focal point of the intensity. You can change the speed and change the focal point of the intensity. If this was light, you cannot change the focal point. I'm now going to get a bit personal. That doesn't mean to say I'm going to get rude, because I've got nothing but compliments for the company that I'm now going to talk about. Along with these diagrams, Steve Walters, who is the owner of a very big American company called American Photonics, puts quite a lot of videos onto YouTube. I've spent 2 or 3 sessions speaking to Steve. He was the only person in my 2-year quest that's been prepared to speak to me about the problems I could see with lenses. Now, he makes lenses. He makes superb quality lenses. He uses the best materials, the best computer programs. He's got some of the finest equipment in America to make his lenses. And he supplies lenses to any and every company you want to name. I mean, the ones that we would recognise would be Epilogue and Trotec. Go and look at his website and see just how many other big industrial companies he supplies lenses to. Now, you can go onto his website, American Photonics, up there, and you can watch this video along with some other very good videos. He has taken time here to look at these Chinesey type pictures of lenses where they don't tell you too much information. And he has realised that there are problems with these lenses. Not our sort of problems, but his sort of problems, where he says, well, these guys are not telling you the whole story because, you know, this 9.2 working range is, for example, shown here, but it only applies to a 6mm beam, not to a 4mm beam or to an 8mm beam. So this is really what he's claiming here, and quite rightly so. This is very limited information and can give you the wrong impression. Well, I've got bad news for you, Steve. The whole of this is giving our laser community totally the wrong impression, because we cannot achieve any of these numbers. Now, the whole of this is based on the imaging principles of lens theory. I have to thank Steve for producing this chart, because it tells me exactly where the discrepancy is between our laser world and his laser world. He makes lenses. As I said to you, he makes the best lenses that are probably available. We use those lenses, and there's nothing wrong with those lenses. The only thing that's wrong with them is the specification. We cannot achieve any of this stuff. This is all based on imaging and not based on intensity. I mean, we've just seen me using a 1.5-inch lens, and we'll go back and we'll use my 1.5-inch lens. But the first thing that I have to say is, have I got a 4mm beam, 6mm beam, or an 8mm beam? If you go and watch the video, which is a very interesting video, by the way, he tells you how to go and find this critical diameter here, which is the diameter of the beam. Okay, now, the diameter of the beam is fundamental to his computer program. He puts the beam diameter in to start with, and then the focal length, and then all these other numbers come out. Now, we don't have a choice. We've got to use these lenses. It's just that people do not understand how these lenses actually work on a laser machine. They do not follow the rules of imaging. I'm going to demonstrate to you very clearly one or two numbers that are in here. None of these are my beam, or are they? First question is, what is this beam diameter? Is it the real beam diameter, or is it the full width at half maximum? I can't believe it's full width at half maximum, because if this is based on light theory, this has got to include every single ray. And as we've seen, if I choose 5mm as my beam width, what about all this crud out here? I mean, this is energy, this is intensity, which is going to do damage. There is this fundamental thing that Steve talks about in here, which is the theoretical focal point, where the two half-angle divergences and convergences cross over. If I move away from this theoretical focal point by 0.2, then I will produce a spot size of 0.042 millimeters. If we can achieve that spot size, we will be able to put down 600 dots per inch. Even with my very, very finely focused compound lens, I can achieve maybe 0.1. On certain hard materials, I can get to 0.05, which gets me to about 500 dpi. They are very special circumstances, and they are not spot sizes. They are dot sizes that I'm able to achieve, which is different to a spot size. And I'll try to explain that to you with a few demonstrations now. We've got a 38.1mm lens inside a nozzle which has got a big hole in the bottom. The lens is buried 10.6mm inside the nozzle, flat side down, which means that for a 38.1mm focal point we need 27.5 gap below the nozzle. The chart recommends that we shift up. In other words, we raise the focus or drop the work by 0.2 to get our first result. Now this is expecting a spot size of something like 0.05. Here's one of my hairs, 0.04. It's a little over a hair's thickness. That's what we're looking for. And I've got a set of spacers here, which are 27, nearly 27.8. I don't think we're going to jump around because of 0.07. Now it doesn't say with or without air assist on that chart, and it doesn't say how long I can afford to burn it. But of course, if it's a focal point that I'm going for, it doesn't matter, because all the rays will go through the same focal point, and it doesn't matter. So let's set the power to full 70 watts. I've got the head towards the back of the machine. I won't change it just in case it affects the focal point. But I'm pretty close to the back of the machine, which is where we had our best results, remember? The least amount of burning and the most accurate results. And here we go. Well, I think we've given it a fair shot. What's your opinion? Does that look anything like a hair's thickness? So here's an Allen key. I don't know what that is, about 2 millimeters diameter. Yeah. A 3 millimeter screw. So I think 0.5 and 3 millimeter are a little bit apart. I know you're going to say that's an unfair test. No, it's not an unfair test. If all the energy was passing through a single focal point, I could not have done that. The only reason I can do that is because the intensity of the light is not focused at one point. Intensity is the key word, because intensity is the thing that does damage to those molecules. Now, I can make a very thin line with that beam set like that. Let me show you. Same power. And there we go, we've got a thin line, but I can tell you that's somewhere between 0.1 and 0.15. I'm not going to be able to get 500 dots per inch out of that lens. The other thing then is, I'll put the speed back down to 50. The point is very clearly made. I've not changed anything except the speed. The power is the same. Okay, I'll tell you what we'll do. Let's drop the power down to 10%. We'll leave the speed at 50 millimeters a second. Am I making my point? There cannot be a single physical focus, because I can change the thickness of that line without changing anything except the speed and the power. We've got the focus set to 37.9. So there's something wrong with the basic idea of using standard lens theory with our laser beam. I would probably say that line there is around about 0.1. But that's still twice the thickness that I was promised from this lens as a spot size. That is not a spot size. So I'm now going to remove the lens completely. So distance has no effect now. I'm not going to put the extractor on, but we're definitely going to make some smoke. Exciting, wasn't it? Now, every one of those was done at 70 watts. Two real questions come out of this. Number one, why are the lines changing thickness as I change speed? And number two, why is the colour changing? We have no lens in there. This is just a naked laser beam. Now remember, a lens amplifies what the laser beam is doing. Thick line after the lens. 400 millimeters a second, thin line after the lens. Now here, the lens is exactly the same focus, but here we have no lens, but we've got the same effect even though we haven't got a lens in. We've got a changing thickness of line and a changing colour of line. I'm going quiet for a few seconds because I'd like you to think about it for a minute. Here's our laser beam, but our laser beam is not a parallel beam of light. It might be parallel, but what's inside that laser beam is a changing intensity. Now, although you can't see it, what's inside that beam is exactly like that little spot of light there. It's very bright in the centre, going out to nothing at the edge, which is what this graph here is showing you. It's showing you zero intensity at the edges of the beam and a very high intensity at the centre of the beam. And that's before we amplify it, because that's the natural shape of the beam coming out of the tube. I cannot state this enough. Intensity of light is the thing that's damaging our material. You can't shine a torch, as I just did, at that material and make it burn. It has to be a special sort of light. It's not normal light. But we've got a distribution of intensity which is not uniform across the beam. When the beam runs slowly, we're able to use this intensity right at the edge of the beam here to do some damage to the material. There's no intensity right out at the edge, but close to the edge we've still got some intensity. It's very low, but we still have some intensity of light there. Given enough time, that intensity is sufficient to overcome the damage threshold of this material and change it chemically. It shakes the molecules into doing something else. So at slow speed we've effectively got a line or a burn which is that thickness, and it's very deep because we've got more power at the centre doing more damage. It's probably a mil and a half deep. And now let's take a look at the other end here. We're up here. So first of all, we're only able to burn that width of beam down here, because we've filtered all the rest of the energy out by virtue of speed. Exposure time. There isn't enough exposure time to do any damage to this material outside here. So we're stuck with a beam that is that width and it's just about marked to the surface. Here it is. Now at the end of the beam you'll see that there are two blobs. Well, that's where the beam starts and finishes. That's where it accelerates up to speed and back down to zero. So we must ignore, and in fact you can see the acceleration of the beam to there and the deceleration of the beam from there. Speed was the thing that was determining the width of that line, as I described here. Now if we take a look at that in more detail, we shall find that right at the top there, where we were producing that line, there's virtually no difference between there, peak intensity, and here, which is the lower intensity at the edge. So we've got virtually no intensity change across here, and so we're doing fairly uniform damage over that very, very small part of the beam there. So this up here is actually darker because it's got more exposure time. But once we start getting really fast, not only have we filtered out all the lower power, what we've done, we've spread this high intensity over a much wider area. In other words, it's, if you like, damage per unit of time. Anybody with any photographic knowledge will understand what exposure time is, and they can analyse why we've got varying colours here. So that's a very simple model of what's happening after the lens here as well. We've got this same speed filtering. So there's the normal spot size for this lens. Fixed focus is an imaging concept. We are not trying to place an image on the surface of this material. We're trying to place intensity onto the surface of this material to do damage. And that's a big difference between the two concepts. Now I'm going to finish up with this diagram because I don't think we need to go any further. We've chosen one point and shown how exaggerated this information is when applied to our laser machines. The lenses work. We have no problem with that at all. We don't have a choice. We've got to use the lenses that are provided. The only problem is that the specification for the lens used in a laser machine is not the same specification as a lens that might be used in a microscope, a camera, a projector or a telescope. And that's what these numbers apply to. They do not carry any concept of the damage that we do to material with different intensity light beams. That's the bit that's missing. And these numbers, you demonstrate how we can get them and I'll buy the lens. I must insist, Steve is a hero. He's a great friend of mine because he's been very helpful and he's produced this information. Every other lens manufacturer in the world is suffering with exactly the same conceptual problem about laser beams and the way they react with lenses. And now that I've worked out what's going on, I can start analysing lenses in a different way, and maybe we can find a very efficient way to use lenses. For example, nobody wants to use a lens that way up. But I suspect in the next sessions that I will prove beyond any shadow of doubt that using a lens that way up is more efficient at cutting than when you use it that way up. So on that interesting note, I will again thank APC for the information and the help that they've given me during this process of understanding how lenses work. So thanks for your time and patience today, and I'll see you in the next session.